Do a little bit of a short explanation. We use induction heaters a fair amount here. Induction heating. It becomes confusing to people when you say you have an induction heater when it's not really an induction heater until you have the whole system. You have a coil that induces electricity into some part you're working on. The heater per se, a lot of times, technically it would be the whole thing, the coil, the electrical power supply, possibly like the one that we usually use over here. This one is rated by the manufacturers. I don't know, can you see it in between the machines there? Okay. The bigger box, the bigger white box is the power supply on this one. The smaller white box is the one that we actually hook up to, and you've seen in a lot of our videos, because it has there's a transformer in there. Both of those have water cooling to them. You have to keep them cool with water because there's too much power going through them for their size to air cool them. Just the plain electronics take water for cooling. Smaller units are air cooled. Like I say, this one's rated at 60 kilowatts. That provides the electricity. And the concept of that is that it provides high frequency electricity. Then your coil that actually puts the power into the part, it is going to be copper tubing, and you run water through it also so that it keeps cold. It needs to be cold both because of the amount of power that you're putting through it and because the part that's going to be hot inside of it is radiating heat out. And with water going through it, like this one here, both of these we've used recently, and you can see this copper still looks nice and clean, even though it had a glowing red 7.5-inch shaft inside of it. So the water really does keep them cool and keeps them from corroding and going away. This one was already weathered colored when I first got it. Well, we also used this one recently. It's not from being hot near it that colored it like this. It was kind of older colored when I first got it. Now this one came with the machine. This is a Chinese machine, and the reason I bought the Chinese machine was pure economics. I bought this one a long time ago, and I see he no longer sells them, from a seller named Timofey, and he still sells stuff. He did a decent job packing it up, shipping it to me. At the time I bought this set over here, they were $5,000. And I don't remember whether it was just over or just under, but it was around $100,000 for a US-made 25 kilowatt unit at that time. And we'll walk down here for a second and see which we have ended up with one of those later because it came up at an auction. And the one that was right around, I forget now what the actual brand is. These are sold, this was sold by Miller, and I didn't price it through Miller. When I was getting the $100,000 pricing was from the actual people that make. You'll see one that looks exactly like this. We'll have to look up and see so we can tag it on there what the actual brand, Rad something I think, but there's a couple different people. Basically most of these are made in England. As far as the, in quotes, US brands. They're mostly made in England. This controller is separate. That's an actual add-on, as is the cooler. The $100,000 when I was pricing it was this unit here, just the one unit. Now, it's been a lot of years since I first bought the other induction heating unit. These on the surplus market are going for between $5,000 and $15,000 generally right now. This one has the additional. And if somebody wants one, they can get a hold of me. I don't really need this. I just bought it because it came at an auction. I threw in a bid. I haven't used it other than turn it on and see that it works. And it was pretty cool for what we bought it for. No, we're not going to sell it for what we bought it for, but in the real market values, like I say, they go for $5,000 to $15,000 now for the base unit. Somebody was seriously looking for one, we would consider selling it. Haven't used it. The thing I like about this better, and why I put in the bid, what I like better than the Chinese one I've got, is it's got the cooler built into it. and the cooler will work with this for the 25 kilowatt output. So it just makes it a lot handier as a unit if we were using it a lot on smaller stuff. As of yet, the other one is currently working. We're still using it. It's wired up, and I haven't had the multi uses of small things. If we were doing a lot of small things again, I probably would take the time to wire and look at using this. This, sold by Miller as this kit, was actually, well, it's the same unit, wasn't sold so much as the idea that you can use copper coils and do high temperature, but was for preheating for welding is what they really sold these for. And this originally was with Alyeska Pipeline, and that was what they were using it for, is with bigger cables for heating a piece of pipeline up to 400 or 500 degrees out in the field, a bigger piece with less heat going into it. While we're talking about that, your heat going into your part, you have got, let's just grab this, drag it over there for fun as a sample. Uh-oh, maybe it's too big. I think I used it for the form, though. I think I used it to form to make these. Okay, let's imagine it's bigger and it's not touching. So basically, what we are doing here, a lot of different descriptions, a lot of different terms in physics that mean the same things these days. Because as we do more and more science, we can't just leave words alone. We want to change them. So I've had some arguments, and it's part of why I decided to go arguments on Bert saying and he just basically said the induction heater works, was basically what he was saying for short. But somewhere in his words, it annoyed someone that wanted to talk about it. And that's why I thought maybe we should talk some more on induction heaters. Now, you have electricity flowing around the coil. And what that electricity flowing around the coil is, it puts electricity going at 90 degrees in the part. If we had a second coil running around in here, we could go from one coil to another, and we could draw electricity off of that other coil. But what happens, as the simplest explanation, is that this piece, being a solid piece, is shorted out. So it's the same as a secondary winding in a transformer, where you'd have two windings, and one has one voltage, the other one has a different voltage, in direct ratio of the number of windings. If you have voltage on a coil here with 1, 2, 3.5 windings, and if those 3.5 windings have 3.5 volts on them, then if we have 10 windings on another coil, it will have 10 volts. If we have 20 windings, it will have 20 volts. If you have one winding, it would have 1 volt. It's directly related. If on this 3.5 coils we had 7 volts, then you'd have 2 volts per coil. So 10 windings would give you 20 volts. That's basics of transformers, which we've got a really cool thing we did with transformer. We want to show one of these. I do electrical stuff too. I haven't mentioned it much, because the more things you say you've done, even though I've spent, many years doing electrical wiring as a job, people say, no, you can't do all that stuff. It's impossible. Stay in your lane. Anyway, as you are putting electricity into here, there's a coupling effect. Is one of the things you have to take into consideration. How well this couples, how well it actually gets the magnetism that drives the electric current. And what we're talking about, this is not DC we're talking about here. It's always going to be an alternating current, a moving field. So a transformer doesn't work with DC. And some people will say a transformer does work if it's pulsed DC. Pulsed DC is essentially AC. And what you do in a pulsed current situation is you put a current in, the field gets stronger, it takes time. As the field gets stronger, it's moving. And when you release the DC voltage, then that field will collapse, it will get smaller, and that is a moving field. And so you will have an AC output from your pulsed DC input. But since your pulsed DC, when you disconnect the current from it, and if you're building a good circuit, you'll have a capacitor across there for it to flow into. When you do that, there's actually current on your primary coil going backwards also. So even the DC pulsed current side has AC on it because of the way you are functioning using the coil. The higher the frequency, the more the energy will stay on the outer portion of the tubing. And someone had talked about that when we were talking about doing the shaft. They said that because induction heaters only do the outside, well, that is the most common thing they're used for, is induction hardening the outside of a part. You can put a very high, very dense current into a piece, heat up just the outside and quench it immediately so that the outside gets hard with leaving the inside still softer. So it's not a chemical change like you do with case hardening. Is a chemical change where you are changing the carbon content in the outside portion of the steel versus the inside. So once you, and you could do both in the same situation. You could do a case hardening, and then as far as the composition of the material, you might do it in a big batch and be such that because you don't want to have a damaged outer case from oxidation, your particular furnaces and things, you might put the case into it where you've got the extra carbon, but not actually harden it at the point that you do the chemical addition of the carbon. So then you could come back, heat it up quickly with the induction heating and quench it. And it would be exposed to the oxygen while you're induction heating it, but only for a short time. So you wouldn't have the degradation you would have if you opened up a big controlled furnace and you had carburized a whole bunch of these all at once. There's points where you can do both together. The more common is you're going to do a piece of alloy that can through harden, but the fact that you're heating just the outside causes it to not through harden, but to harden only on the surface. These coils also don't have to be round this way. They can be pancake shaped. And I guess actually, let's go out here for a second. Let's walk out to our stack of coils we've made for various jobs. We have some pancake ones we've done. We did a sprocket that was 22, 23 inches in diameter out of hard plate. And we annealed it originally, and then we rehardened it afterwards. It was made out of AR 500. And so we got just a variety of some coils we've made over the years. The one, well, here's another coil over here actually too. When we bought that Chinese induction unit, it came with 3 coils they would wind for you for free of whatever I wanted it for. And I initially had bought it for doing foundry work for bronze, which we've never used it for. And I bought some crucibles, and I told them what size crucible, and I haven't actually even pulled these around the crucible to see if they fit correctly. But it was a free portion that came with the unit, so it seemed like the thing to buy. When you buy it, one of the descriptions of your 3/8 OD tubing is actually 1/4 inch L, because they go by an approximate of the in size, and the L is the thickness rating. So copper tubing, they talk about it both ways, by OD and by ID. Most of your fittings go according to the OD, and they try and make it sizes so that the OD is a nominal size, even if the ID is what they're referring to for size. Much like pipe. Okay, now let's say we don't want to heat the outside. Let's say we want to heat that shaft like we did. And let's say that when we want to heat that shaft, all we're stuck with is a high frequency power supply. So it only heats in here well to the first 1/4 inch. And also, on a side note is, when your steel starts getting quite hot, when it gets past the point of being magnetic, which with your steels where that really changes a lot is around 900 degrees. You get it hot, and it varies with alloy, but so don't yell at me for that number. It's not a definite number. But anyway, you will notice that when your steel is no longer magnetic, it doesn't have as much of a countermagnetic fluence. And what that is because of the magnetism that the steel itself absorbs while the magnetic field is moving into it, it takes time for it to move in because of that absorption. Once it gets hot enough so that the steel is no longer staying magnetic in a definite polarity, the electricity actually goes into it quicker because it can switch the field. It's just electrically conductive at that point. It's no longer magnetic. It's no longer getting set as a temporary north-south this way, then south-north the other way, and back and forth. While it holds its magnetism as the cold steel, it takes more time to get the power into it. That's part of the coupling. So, point being again, back to the shaft. Darn it, it's only quickly making this hot 1/4 inch deep, and then it starts getting too hot. Well, you pulse it. There's a thing called an on-off switch. I just manually pulse it. You shut it off, you let the heat soak into the shaft, you heat it up, you let it soak in, and after doing this for several years, where we've done other tests and things, you kind of know how much heating on the outside and how long to heat up the whole shaft deep enough. And we didn't really even need to heat the whole shaft all the way through for what we're doing. We only needed the first 1.5 inches heated up to get our weld fully normalized. So now, let's say that we drop the frequency down and the heat is more general through the whole part. Slower frequency, which is the same thing again, the magnetism can go through further because it doesn't have to fight that change in the magnetism of the piece we're magnetizing. A thinner piece will magnetize quicker. A thicker piece, slower frequency will let it go thicker, deeper into it. It doesn't have the skin effect so much. So I don't know, I've been curious to try this, is bring some, just use transformers, come off of the 60 cycles and try some induction heating just strictly with the 60 cycle. They do that for some large foundries. They just straight use 60 cycle. It's supposed to have a lot of mixing. And I don't know if it mixes to the point. The information on it is a little sketchy when you start studying it because people that were doing that were mostly a long time ago. Most of them today are using electronic controls and they can pick whatever frequency they want, whether it's 200 or 1,000 cycles for the lower end, or whether they want 20,000 cycles. They also can pick the cycles, start at 20 and work your way down. The lower frequency does some mixing of the metals, which is an advantage. But the big thing is, does 60 cycles when we're doing a foundry actually throw pieces out of the crucible? It might. I don't know how dramatic it is. I have not done it, but I've been interested in trying that someday as far as something to try. Now, I think I kind of described some of the basics. There's some beautiful books on induction heating. I've got a couple of them. I don't have the titles of them right off. You can find them. That is what the internet is the best for. It is the best for finding good old books. Sometimes you got to search a little longer to actually buy the old book because it may not be on a pretty darn frustrating PDF format. And I'd say that. Actually, PDFs are pretty good these days. I like them. But when they first came out, they were pretty darn frustrating. They were. They were just glitchy for the first few years that they had them. But I've been using them for, I don't know, 25 years or so now. They work pretty good. Early, I came up with the name PDFs, though, pretty darn frustrating, because that was what they were every time I wanted something. People are going to ask, what do I think of the Chinese, this particular Chinese power supply? There's a lot of less expensive ones they've got out there, lower output. There's two things I don't like about it. The minor one is that it is frequency non-adjustable. It picks what is the best frequency it thinks for the coupling, according to your shape, your length, everything. So it will couple into a part somewhere, but you really can't control it. And you can't really turn it up to where, okay, we have a bad coupling and I'm putting 9 kilowatts into this part, but I want to put in 18. Can I tweak it and go higher? Can I do something to get? You can't. You have no control. A lot of the older US ones, and I don't know about that Miller one I've got down there. I haven't really played with it, how adjustable it is, but you could adjust your frequency. And when you get too much power on it, it gets too hot, it gives you a warning. Will Robinson, quit. So, you know, that I like better. I'd rather be able to at least choose it so that, you know, I want it in this range, but it does heat things up. It does work. I've done a lot of stuff with it. I haven't used it for foundry work yet, which is what we originally bought it for. And since that project is on permanent hold right now, we may never do a foundry with it. We might do foundry with other, we probably will do induction if we do a foundry. But I don't really have the space here. And my plans on all of that has changed a little bit. But the other thing, which I totally hate about these, is the cooling circuit. In the main electronics, the cooling circuit will not come on unless the flow switch shows that you have flow. And if it was an actual flow switch, that would be good. It's not a flow switch, it's a pressure switch. So what you have to do is feed it pressure, and I think it's around 30, 40 psi when it comes on. But we just play with it. We feed it full water pressure that I've got here, which is about 60, and then we close the outlet down enough to where the switch will come on. Because I can have really good flow through it with the water open and just controlling the volume. The switch will never come on and let it run. I could bypass the switch. I hadn't done that, and an actual flow switch would be nice. So that I don't like about their water system. The other one I don't like, the water that comes out of the main electronics then flows into the transformer. I could probably split this or do another hose and just let the electronics drain out, do a separate hose for the transformer. But the transformer is the part that seems to get more of the heat. And the hoses from these people don't like the heat that it should be able to like. So fortunately the blowouts have been in the transformer, but we've had about 5 times that we're in the middle of a job and all of a sudden it goes whoosh, and water starts spraying everywhere inside the transformer. We go kill the main power because you don't want to be anywhere near a 480 volt wherever it's got water spraying around. We go kill the main, and they don't, you have to talk to them and request one that's 480 volt if you want 480. Most of these are 200 volt class or 380. And I'm a little sketchy on that, whether they really built me one that's for 480 like they said, or whether it was just a 380 one they decided would be good enough at 480. It works at 480. It has a sticker on it that says 380, and then they added 480 after that. It works. It's been working at 480. I wouldn't want to try one just rated for 380. But the hoses, the water hoses in the transformer, that's my biggest complaint. They're, to the US market anyway, a strange metric fitting. I don't know how to get different fittings to get different hoses to go on there. I bought some generic Teflon hose that should take whatever it needs, because it's the copper next to the hose itself is not getting hot while it's got water running through it. It's the transformer, and you can tell it really is not getting, it's only getting up maybe 250 degrees or something, and it's popping the hoses. So it's not like the unit is putting out too much heat, it's just too much for the quality of the hose that they used. When I bought this in what year did I buy it? 2012-ish? I'm not sure. So they may have better hoses now. They may have gotten this complaint and fixed it, or maybe other people don't use them as hard as I do. Now again, also back on the other hand, with the coupling, with not being able to adjust it, this is in quotes a 60 kilowatt unit. The best coupling I've ever got was about 35 kilowatts. So on the one hand, that's good, because if I go over 50 kilowatts for 15 minutes, my electric bill costs me thousands of dollars for that month, the way our utility works here. So we go out and we watch the utility meter whenever we use it, just to be sure. That's why I bought a 60. Had I known the coupling factors and all of that, I probably would have spent a little bit more and bought the 100, I think, was not that much more at that time. I probably would have bought the 100, trying to get more capability out of the unit, because that's a nominal rating. And you're going to have that problem whether it's US made or China made. Where it's aggravating to me is that I don't have the individual control of the frequency and what is going wrong, so that I can try and remedy the situation. There are some remedies that are mentioned, as I say, in some of those good books on induction heating, and I'm not an expert on it, so I can't tell you everything that was in the book. If I was having major problems to where it wasn't working, I'd go back and read one of my books again. So I think that's pretty much it on this unit. Oh, there's another thing too with the Chinese unit is their terminals, they have a cover over them that is not considered safe by US standards. The cover is hinged. You have nice bolt-on lugs. There's a hinged cover, but there's nothing that holds the cover down. I would suggest you either add something to hold it down, or be very, very careful if you just use it intermittently. Now, we have another thing over here, which is not part of the induction heating, and